Hello, ma'am. Nag-start na ka, ma'am.
Yes, start na po. So, balik na lang sa pagdirig. Okay, I was saying earlier that if in the future you really would like, you love organic chemistry, love synthesis, no, because it stimulates your mind, no, to find new reactions, new pathways, and using new catalysts. And this one actually, this guy Sharpless was actually able to win the Nobel Prize in chemistry, and there are countless, no, chemistry is evolving, discovery of new organic substances and pathways is always new, and scientists are always looking for an improved pathway to do synthesis, especially for compounds that would be beneficial to mankind. Okay, and sometimes it may not seem to be that beneficial at all, but then that compound that you may create or produce will be a starting material for another reactant, a starting material for the synthesis of another product, which should be beneficial. So for example, this one, it involves the enantioselective synthesis of the side chain of the anti-cancer paclitaxel. Serves to illustrate the Sharpless catalytic asymmetric dihydroxylation. Okay, so one of the when scientists or chemists actually are handling very large compound, no, so to produce or to make that large compound, no, there are a lot of synthesis that's being involved. So for example, in the production of paclitaxel, you have here, there is this part here that is being produced, this one, and this one is paclitaxel, and how it's being used, you have to produce something like this. So before it is added to the paclitaxel, this one, the production of this product, no, from the catalyst that's being discovered to produce the hydrox 1,2-diol rather, no, as a precursor to, or as a reagent to proceed with the reaction of the paclitaxel, which is an anti-cancer drug. So it's a very large one. Anyway, so let's proceed to the cleavage of alkenes, which is another reaction of alkenes. No? So for us to cleave the alkenes, to do oxidative cleavage, no, aside from the osmium tetroxide, where you can have your diol, it's an oxidized form of your alkene. No? You get oxygen to the carbon. Whenever you get an oxygen to your carbon, when initially carbon is no oxygen, it's already an oxidation process. So in this case, alkenes can also undergo oxidative cleavage. Our agent here is ozone, or we can have our hot potassium permanganate. So we already know that potassium permanganate is a strong oxidation reagent. It's needed, and ozone is you can when it's hot, okay, you need potassium permanganate. You also need ozone, the O3, as your reagent. Okay, so let's proceed. So how does it happen? How does the cleavage proceed? You have to treat it with hot basic KMnO4 to cleave the double bond of an alkene, and cleavage is actually believed to occur via cyclic intermediate rather, similar to what you observe with osmium tetroxide, where you form an osmic ester. So alkenes with monosubstituted carbon atoms are oxidatively cleaved to salts of carboxylic acids, and disubstituted alkenes, carbons, are oxidatively cleaved to ketones. So if you have disubstituted and unsubstituted alkenes, are oxidized to carbon dioxide. So depending on the kind of alkenes that you get, no, you can oxidize that to ketones, you can oxidize that to carboxylic acids. Pag monosubstituted lang, you can actually have carboxylic acids. Pag disubstituted yung alkene, you can have your ketones, and pag terminal alkene, unsubstituted, you can actually get your carbon dioxide. Okay, example, you have your alkene here, whether cis or trans, and then you add KMnO4 in basic medium and hot KMnO4 in basic medium, we can actually oxidize the double bond here to get your C double bond OO. Since it's basic, you don't get C double bond OOH, no, because since it's basic, the OH, the proton here from the carboxylic acid will be deprotonated, abstracted with the hydroxide here. So you don't get a COOH. You get the conjugate base of the carboxylic acid. Carboxylic acid, you have the C double bond OO by the C. Okay, and once you have that, you can acidify this one because we did do this, perform this one in basic medium. You can acidify and you can protonate this one to produce your acetic acid, this one, or abstract rather the proton from the hydronium ion, and you recover your acetic acid. So if you have, this is a, what kind of alkene this one is? Disubstituted, okay? Or disubstituted alkene, but you have monosubstituted carbon, kani. Your carbon is monosubstituted. Kani nga carbon, nanishik kani. Kani nga carbon, substituted na siya ani. So you get your carboxylic acid. Since this is symmetrical, no? You just get one carboxylic acid. If you have to flip this one, you get CH3COO gihapon. This one you have CH3COO gihapon. Then acidify, you get your 1,2, which is ethanoic acid, or your acetic acid. So this one, this carbon here is mono, 1, 2, is disubstituted. Pag disubstituted in the presence of KMnO4 and hydroxide basic medium heat, and then acidify further, what you can actually get is kani a ketone instead of C double bond O. Okay, kani C double bond O, what you get is C double bond, instead of C double bond O, OH, kani, what you get is C double bond O lang. No, it's impossible for us to have an OH since this is like carbonyl-carbon secondary siya. Okay? Pag unsubstituted ang carbon, like this one, there is no R group. What we actually obtain is carbon dioxide, CO2. And of course, water here in the present. So two steps for this kind of reaction. The result is the second step, which is the acidification. If you don't acidify, we just get the conjugate base of the acid. So we need to acidify. So here, this is what he said, that unsubstituted alkene carbons are oxidized to carbon dioxide. Okay, and disubstituted alkene carbons, like kani, disubstituted siya, you have your R, another R here, you have your methyl, another methyl here. So disubstituted kani nga carbon, we don't look at the whole alkene, but we look at for every carbon. Then you get your ketone. Okay, in this one, this is mono, you get your carboxylic acid. Okay. So the use of, one of the use of KMnO4, other than oxidative cleavage, is a test for unsaturation of an unknown compound. So similar to the bromine, no, in the presence of that carbon tetrachloride, an organic solvent, you can use KMnO4 to test for the unsaturation, the double bond. If an unknown compound or an unknown solution has a double bond, you can use KMnO4. So if an alkene is present, the purple color of KMnO4 is discharged and a brown precipitate. So we use KMnO4. What happened is that we actually, this is an oxidizing agent, no? If ma-reduce niya ang alkene, kung saan niya pag-reduce, it's either, at least atong alkene, i-reduce niya to, i-oxidize, this is an oxidizing agent. I-oxidize niya to either a carboxylic acid or a ketone, or pag-terminal, pag unsaturated carbon sa double bond, no, you get your gas, carbon dioxide gas. So if an alkene is present again, you use an oxidizing agent. You oxidize niya ang alkene to the ones that I mentioned, either carboxylic acid, ketone, ketone, and carbon dioxide if unsubstituted, and then i-oxidize man niya si alkene, kani si KMnO4 will be reduced by itself. No, it will be reduced to MnO2. So pag ma-reduce MnO2, sa mahitabo, KMnO4 is purple, Pag ma-reduce siya, this is our oxidizing agent. Kani MnO2 actually is a brown precipitate. So the oxidation state of NO4 is 4, 2, negative 8, minus 1. So that's positive 7. When it is being reduced to MnO4, its oxidation state for manganese will become positive 4. So positive 7 to positive 4, there's a reduction process. It came in O4 while the alkene is being oxidized to carboxylic acid, ketone, or carbon dioxide. So it's up. So ang atong indicator dili sa alkene atong gitan-aw diri atong gitan-aw is the reducing is the oxidizing agent. It came in O4 being reduced to MnO2. Pag makita ta brown precipitate, then we could say that there is an alkene present. Katong isa ka reagent that's being used for the unsaturation of the unknown solution, we use Br2 or bromine, which is colored, sa color ni bromine. So, kita color ni bromine, may pagkakuan siya, may pagka-purple pag siya si bromine. Okay, and in the presence, kung ma-react sa bromine with a double bond alkene, then wala ang coloration. So, from purple or brown, may pagka-brown, red-brown na si bromine, ma-colorless na. So it means that na-consume si bromine. So there are two tests that you can see in the lab, whether there is an alkene present sa imuhang unknown solution. You can use KMnO4 as a test for unsaturation, and you can use the Br2 in the presence of an organic solvent to test for the unsaturation. Okay, so going back, the oxidative cleavage of alkene has also been used to establish the location of the double bond in alkene. So if we do oxidative cleavage actually like this one, we can actually know nga asa dapit ang alkene. So if this is our product and this is what we get, this is our product that we obtain from the reaction of our alkene, this is actually used to establish the location of the double bond. So you can see here, nga oy naaday siya double bond during the pita, and there should be a carbon before this oxidation happens sa iyang reactant na din double bond somewhere here with another carbon, since CO2 man diri okay, walay another ketone or walay kani siya. This means that CH2 na siya, and so this kind of reagent is actually used to determine the position of the double bond sa dapit sa imong reactant. Okay, let's have an example. You have, for example, an unknown alkene with a formula of C8H16, and when you oxidize that one with hot basic KMnO4, it yields a 3-carbon carboxylic acid. 3-carbon, 1, 2, 3, like propanoic acid, and a 5-carbon carboxylic acid. You have 1, 2, 3, 4, 5 pentanoic acid. The question is, what was the structure of the starting alkene? You have to remember that when carbon is monosubstituted, it can actually, the carbon in the double bond, when it's monosubstituted, you can actually get a carboxylic acid. Pag disubstituted ng carbon, you get a ketone. Pag walay substitution ng carbon gikan sa double bond, then you get a CO2. Okay, so in this case, you get a carboxylic acid, So most likely, there is a double bond somewhere here and a double bond also here. So you have 1, 2, 3, 4, 5, 6, 7, 8. You have here. Can clip this one. Connect na nimo sila kani si, let's say, let's color it red. This one is green. Connect nimo na siya. Get a double bond between this two here. So you can count 1, 2, 3, 4, 5, 6, 7, 8. Okay, and of course, the other one is the other agent is acidification. So your answer, and unknown alkene, what is the structure of the starting alkene? You have 1, 2, 3, 3 octene. Okay, so it's very simple, and this is what was being said earlier, that oxidative cleavage of alkenes will determine kung sa asang position of the double bonds. You just have to be mindful, or whether your alkene is like this one. You can see here is monosubstituted. In this carbon, you have a hydrogen and there is one R group. On this carbon, you have a hydrogen here, wala kita-kita, and you have this R group. So it is monosubstituted. Pag another R group diri like say another CH3 or another alkyl group, no, you don't expect the other one to also like this. Instead, you will get a ketone. Okay, so you just have to be mindful whether your carbon in the double bond is substituted or not, or were it substituted or not, or how many substitutions, or whether it's unsubstituted. Okay, so let's proceed with so what's in here? So cleavage with ozone. Again, it says here that the cleavage method with ozone is very useful, no? Or ozone is, or the most useful method for cleaving alkanes is to use ozone. It's a very important reagent. And to do that, so kanina we're using KMnO4, no? Alternately, we can also use actually ozone. And in fact, ozone is stated here the most useful method now for cleaving alkenes. So how do we do this ozone? When we have ozone, we call this one as an ozonolysis. So sa ozonolysis, we know ozone is a gas, no? It's a reaction between an O2, or it is prepared from the reaction of an oxygen, diatomic O2, and a radical O that produces the O3 ozonolysis. The ozonolysis consists of bubbling ozone into a very cold solution of an alkene. So we have to do this at a very, 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 very low temperature, which is -78. So imagine your refrigerator, know how low can your refrigerator be made. No? So to do this one, I think they have to do this, the equipment that they use. They also use this with nitrogen, I think, not to make the temperature very, very low, or they have a freezer that could reach up until -78. So we bubble the ozone into the alkene in the presence of organic solvents, H2Cl2. So that's the common organic solvent. H2Cl2 is very unreactive. And then followed by the treatment of the solution with dimethyl sulfide, or if there is no dimethyl sulfide, you have here Me2, say dimethyl, you have CH3S, CH3, duha ka CH3S, or if there is no dimethyl sulfide, you can use zinc or acetic acid. Okay, so that is our agents. So the overall result you have here, this is your carbon, which is di-substituted, RR, and another carbon, which is mono-substituted. Now you have carbon R. Okay, you have hydrogen. So what we get actually on this side is the ketone, but this one, this is mono-substituted, we don't get a carboxylic acid. Or supposedly you have your hydrogen. This is, remember in sa tong KMnO4, no? If mono-substituted lang, we get a carboxylic acid. But if you use ozone, we can only oxidize up to an aldehyde here. So C double bond O, and you still get your hydrogens not being replaced with OH. Okay, so as our agent again, your agent is ozone in the presence of dimethylchlorine, dichloromethane rather, at a very low temperature. And second step is the use of dimethyl sulfide. So you just have to remember your agent whenever you have a reaction. So the reaction is useful as a synthetic tool as well as a method for determining the location of the double bond. So there are two reagents that you can use to determine the location of the double bond. One is the KMnO4 in basic medium. And this one, and another one is the use of ozone in dimethyl chloride, and you have your methyl disulfide. So the overall process results in cleavage at the double bond with each of the carbon bond becoming doubly bonded to oxygen. So you just have to take note, carbon will always be doubly bonded to oxygen. So wala na yung madublang OH. Unlike your katong ginanako with KMnO4, Instead of hydrogen here, you get your OH. Now this one, kung diri mag-cleave, now you get your cetyl bond O here. This is the ozonolysis. This is the difference between Chem and O4. What else? So let's have another example. You have 2-methyl-2-butene here. You have ozone in CH2, CHCl2, your dimethyl dichloromethyl, no? Permiticulag. Dichloromethane. A very low temperature and Me2S. So what you get the double bond here. C double bond O, you have your acetone, and C double bond O, you have your aldehyde, hydrogen. You have your double bond here. What you get is C, kani, copy, C double bond O. You have your aldehyde because this is hydrogen here. This is one substituted. You have hydrogen, and double bond here. So you get your C double bond O and hydrogen. Okay, so you don't get your carbon dioxide where you have your C double bond O. So you can only get your carbon dioxide pag KMnO4 ang imong magamit. And this one, pag KMnO4, dili aldehyde imong makuha, but carboxylic acid. So you just have to take note on the difference on the cleavage of the double bond when we use ozone or when we use KMnO4. So the problem, give the structure of an unknown alkene with the formula C7H12 that undergoes ozonolysis to yield with the formula C7 that undergoes to yield after acidification only the following product. Okay, so what we have here, C7, you can count here 1, 2, 3, 4, 5, 6, 7. Yes, so you have your product here 1, 2, 3, 4, 5, 6, 7. So but you get cetyl bond O. So what does it mean? And you have your reactant C7H12. So most likely you have 1, 2, 3, 4, 5, 6, 7 naman no. So most likely this kani siya isa ra pud imuhang reactant. So most likely cyclic imuhang reactant diriya. And you have kani ug kani nag-double bond. And you will have, you can write on cyclic compounds 2. So you see here, you have C212 minus 2. You have a 2 degree of unsaturation. So you have a double bond cyclic. You have here, isumpay lang ni siya kani o kani, double bond. So you have 1, 2, 3, 4, 5, 6. Kani man siya magsumpay. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And then nakay kani, sa double bond ni mo nakay kani. Cyclic. So pag isa lang ganin yung product na makita, it's either cyclic siya or it's either symmetrical, more yung tanawon. But since ang giingon diri kay C7H12 man, so 7 naman siya, so it's a cyclic one. So i-cleave lang din mo ang cyclic and you get 2 aldehyde, ketone and aldehyde here. Okay, it's very simple. So for the mechanism of the ozonolysis, it's similar to osmium tetroxide, no? So what happens is that kani parehas sa katong kung gipakita ka ganina, no? Wala gipakita ni kinsa pa kanin si author ning book si ni Solomon, but you will have this. You will have your double bond, no? Will be added to your oxygen, and si oxygen kay mo form siya bond dinhi manobra na ihang bond, so it will convert the bond here to an electron pair diri, and pag form yung electron pair diri, you will actually have your kani forming a bond. Okay, so what happens is that you get a 5-membered ring. You have your ozonide. Once you have your ozonide, what happens is ma-break ni siya, no? Pag break ana niya, this is very unstable. Okay, kani paingon siya dire. Okay, this is very unstable. So what happens is kani breaks ani niya to form here, and then kani break diri, and then kani mo break diri. Okay, you get your double bond, you get your kani double bond, and you have kini. Okay, so once you have this one, what will happen is you have this, they will be adjacent to each other. No, they will attack kani CO, kani negative. No, to attack this one, and this will attack this, and you get again another 5-membered ring. Pag attack niya ani, okay, manubra og bond, gamiton niya ni to form a bond here, manubra og bond, i-convert niya yung double bond to here. So what you get actually is the ozonide. This is the initial ozonide. When the initial ozonide that you get is carbon-carbon silingan to each other. And ang tulo ka oxygen is katapan. In the second step, or probably third step na ni siya, no? What you get is kani sila. Once you get your product, more react further to form this ozonide. Nga si oxygen is in sandwich sa duha ka carbon, and you have here. And then you have your dimethyl sulfide. Okay, so what happens is that you will get your C double bond O, and then you will have your C double bond O here. So what happens? See, oxygen, one of the oxygen, no, it will attack the sulfur to get your sulfoxide S double bond O here. And ma-break na siya nga bond. This one will form here. Kani ma-break na siya dito. And kani, what happens is mo form siya o ma-attack siya kung sulfur. Okay. And this one also, pag form niya og kung butang mag-araw. Sa manisik ko, dili mag... Okay, wala gid tangag araw ni si Solomon, no? So what happens is this one you will have this okay, so this one you will pag-break na niya, no? So kulangan na ni siya og bond it will be depleted. So what will happen is that this will react to the sulfur. And then what will happen is that kani will be broken to have here. Okay, so you will get your carbon double bond O and carbon double bond O here. And then you have your methyl sulfoxide. You have SO minus, it will be minus, but what will happen is that you get actually S double bond O. So in the end, you will get your aldehyde and your ketone in this process. Aldehyde or ketone aldehyde or ketone. Depends sa inyong initial working. Okay. Practice. So this one will be a problem set. Now, but we can answer number 1. You can answer number 1, and B and C will become your problem set. Can you have a volunteer? So this is an ozonolysis. Here they have 2 reagents. So predict the products of this one. It's very simple. What is your product? 2 products. You get 2 products here. What is your product? Shaira. Wala si Shaira. Or we can call Mary Japer. Wala gihapon si Mary Japer. We can call Arnel. Letter A, Arnel. What is your product?
Yes, ma'am.
Yes, that is your product
Ma'am.
sa
Letter A.
letter A. Ambot asang ubang mga tao.
Wait, ma'am.
Kita ninyo?
Ay. Wala mo makita, ma'am. Pwede balik, ma'am. Wala makita.
Okay. I was checking kung naabay. So what you get, a ketone or an aldehyde? You'll break your bond. You'll break your double bond. You'll cleave your double bond, right? And sampayan nyo na, no, it will be oxidized to become a ketone or an aldehyde. What is your product? Sa'yo naman ang ozonolysis. What is your product? Okay, kopyahan na to ang 5-membered ring.
Carbon pentoxide.
You will have your double bond here. Okay, have your oxygen and you have 2 carbons. Kana, kopyahan ninyo. And oxygen. Kopyahan na ninyo. Now you have your oxygen, of course, kana siya, there is a hydrogen there. So you have 1, 2, you have CH3, C double bond O, hydrogen you have here. So you have 2 types, you have a ketone and you have an aldehyde. Kana remember. Okay? Dali ra ang analysis. Kasi pangalan ni, you have 1, 2, you have ethanol, right? 1, 2 ethanol. This one is cyclopentanone. You end with on. So this is a ketone. So this is 1, 2, 3, 4, 5 pentanone. But this cyclic, you have cyclopentanone, and this is 1, 2, 3, 1, 1, 2. 2 carbons, you have eth, and an aldehyde, you have ethanol. Okay, so it's very simple. So for the rest, katong duha, you will do that as a practice. It's a problem set. Akong i-upload after our discussion today so you can work on Friday for problem sets. Okay, so let's go on. Let's continue with our discussion. Sindugay ko mag-discuss, no? And you have another problem set. End of the slides. So we will continue with the other reaction. Katunatakang alkynes. I have here 30 slides, so 30 minutes. We can have 30 minutes of discussion for the part 2. And in this case, we'll be talking on the reactions of our alkynes. Okay, so for alkynes, you have similar reactions with your alkenes. You actually have a bromination or addition of your bromine to your alkynes rather. So what you get is, if you have a double bond, remember your alkene, if you have your PR2, you get your vicinal dihalide. Okay, so what you get here also is a dihalide, but an dibromoalkene if you have your bromine as our agent. And further, another mole of your bromine, you actually get a tetra haloalkane, or tetra, for this case, bromine, so you tetrabromoalkane. You have chlorine, you get your tetrachloroalkane. Okay, so you notice that you get 2 moles, 2 moles, 2 moles of that in order to saturate your carbon with your halogens. Okay, so this is an example of another example of the addition of bromine to your alkene. You just have to take note that in the addition, what we notice.
Excuse me, ma'am.
Yes.
Kanang wala nagliw kang screen sa imo, ma'am. Na ma'am, thank you.
Okay, so again, I have said earlier that you get 2 moles addition of your alkene, no? 2 moles of your